Pre-Cal 12. Here we go. We're going to look at inverse functions. So what is an inverse? First off, we'll remember that an inverse is an operation you do to another operation that gets you back to where you started. So the inverse of subtraction or addition is subtraction. The inverse of multiplication is division. The inverse of squaring is square rooting. When one does something, the other one undoes something. So functions also have inverses. So if we have the function f of x, we have its inverse written f negative 1 of x, which means f inverse f of x. This does not mean exponent, okay? F negative 1 of x does not mean 1 over f of x, because remember, 2 to the negative 1 is equal to 1 over 2. That's not what's happening here. This means inverse of x, not reciprocal. So remember that one, because that's a bit of a pitfall. Now, where I say there's a zipping and an unzipping, right, and one undoes the other, if you have f of x and f inverse of x, and you make a composite function of the two, you get this relationship. If you have f of f inverse of x, what you get back is you get back x, you get back the input. So basically the two function values essentially cancel each other out. And if you take the f inverse and you plug in the original function, what you get back is x. If you get that scenario, your two functions are inverses of one another. So a bit of a recipe to find here. First thing to do, make sure your function is a one-to-one function, your starting function. Because if it is not one-to-one, you do not have an inverse that is a function. You can have an inverse equation, but it's not necessarily an inverse function. So make sure your original function is one-to-one, and sometimes you may have to restrict the domain, which you will see in a couple of our examples. And then we follow this recipe. We replace f of x with y, or g of x or h of x, whatever. We interchange the x and y's. We solve the equation for the y, and then we throw in the inverse symbol. So a lot of recipe to follow, but you'll see in these examples how that works. So here we go. Here's my original function. So first thing, is it one-to-one? It sure is, because it is a linear equation, right? That's a straight line, so it's definitely one-to-one, so I know I can get started. So I take my f of x equals 2x minus 1. I substitute f of x for y. I swap my x and my y value. And you'll see in an example later when we have multiple x's. And then we resolve for y. So I'm going to add 1 and add 1. So now I have x plus 1 equals 2y. And then divide everything by 2. We get y equals x plus 1 over 2, which simplifies to f inverse of x is equal to x plus 1 over 2. So there is your inverse function. So what we have to do, though, is we have to check. We have to check, is it indeed an inverse? And we check that by first trying this. We throw our inverse function into our original function. So that means for this x in here, we now have 2 times x plus 1 over 2, and then minus 1. Well, 2 cancels with 2, we get x plus 1 minus 1, which means we get x. So far so good. But now we have to check what happens when we throw our original function into our inverse function. And in this case, we're throwing the 2x minus 1 in for the x here. So we have 2x minus 1 and then plus 1 over 2. Well, that gives us 2x over 2, which, yes, please, x. So we are good. We get that x equals, we get that x equals, we know we have an inverse, and we are done, we are happy. So there's a relationship between the domain and the range of a function and its inverse. You can see that the domain of your regular function and the range of your regular function, your initial function, exist in their own little realms, right? But it means that the domain of your inverse is the same as the range of your original. And it means that the range of your inverse is the domain of your original. It is a very helpful piece of information that we can use to simplify the way we look at things. Also, it allows us an opportunity to restrict a domain if necessary. So let's look at this one, because here we have a function, g of x is equal to root x minus 1. Now here we have a domain restriction. X has to be greater than or equal to 1, because we know that from the fact that I cannot have a negative value in my radical. And what that relationship with the range does is it means that the range of my inverse will be y is greater than or equal to 1. So we'll leave that for now. We'll come back to it, because it's not always easy to determine the range of a function. In this case, we can, because when x is 1, y is 0, and then I'm only increasing. So here I can say my range is greater than or equal to 0, which means that my domain here is x is greater than or equal to 0, and that is going to come in handy in just a minute. So let's start by solving for our inverse. So g of x is equal to the square root of x minus 1. Y is equal to the square root of x minus 1. Square both, or swap my x and y's. X equals square root of y minus 1. Square both sides. X squared equals y minus 1. Add 1 to both sides. X squared plus 1 equals y. I'm done. So g inverse of x is x squared plus 1. Part 1 finished. Now what we have to do, though, is we need to check our solutions. So the first thing we're going to check is we're going to check g made up of g inverse. And what we get here is we get the square root of x squared plus 1 minus 1, which means the square root of x squared. Now, since you are taking the square root of x squared, I want you to consider the square root of 2 squared and the square root of negative 2 squared. Both of those will give you the square root of positive 4. Both of those will give you the answer 2. So that is why we say we have the absolute value of x, because the positive and negative values of x will produce the same result. But it's important to now come back to our domain restriction. So we're only actually going to consider positive x values. So that means we get the answer just x. We disregard those negative values, which is super important for making sure we have an inverse. That domain restriction allows us to have that inverse. But we still need to check our other way to make sure everything fits. So now we're going to check g inverse of g of x. So now we have the square root of x minus 1 all squared plus 1. So I've plugged into this guy, right? That was my inverse function. The square and the square root cancel each other out. X minus 1 plus 1, x. Nothing to worry about there, so we're good. So due to this domain restriction, I can say that I have inverses. And if you want to plug these things into Desmos to have a look, we'll do that in class. You can look at it, and then you can see how it won't work until you restrict that domain. So we're going to do this next one here. Now this next one is fully loaded. It's going to take 2 slides. I'm going to start by just solving for the inverse, and then I'll show you the algebra of checking your solution after that. So you can see in this example, I have 2 x's, so that's going to give me a little bit of bonus to deal with. But we also have a domain restriction, because I cannot have 0 on the bottom, so that means x is not allowed to be 3 over 2. So what that does for the range of my inverse is y is not allowed to be 3 over 2. So you can make that connection right off the bat. Now I can't get the range easily here, so we'll wait and see what happens. So h of x is equal to x over 2x minus 3. So that means y is equal to x over 2x minus 3. Now I sub my x's and my y's. So x equals y over 2y minus 3. And now we have to do a little bit of algebra. So I'm going to multiply both sides by 2y minus 3, because that's going to cancel that one. And what that does is it gets my y's out of the denominator. So now I have x times 2y minus 3 equals y. And now I want to get my y values together, but one's trapped. So I need to water bomb that x in to free it. So now I have 2xy minus 3x equals y. And now I can get my y terms on the same side of the equal sign. So now I have 2xy minus y. I've subtracted y from both sides. And then add 3x to both sides. Because now I have my y terms together. And what I can do is I can water bomb or reverse water bomb out, factor out a y value. And I'm left with 2x minus 1. And now you see you can have y isolated, divide both sides by 2x minus 1, and you get your new function. My h inverse function is 3x over 2x minus 1. And now here's where that relationship comes in handy. Here I have a domain restriction. X is not allowed to be 1 over 2. So what that means is I can now complete this domain and range for my inverse, but the domain is the range of my original. So I can actually complete the range of my original function as well. So you get that relationship to determine the domain and range of both your inverse and your original function. So now what we'll do is we'll do the complicated, well, slightly complicated algebra to prove that they are in fact inverses. So we had h of x was equal to x over 2x minus 3, and we had our inverse h of x was equal to 3x over 2x minus 1. So the first one we will do is we will do h of h inverse of x. So everywhere I have an x, here and here, I have to plug in this big fraction here. So now I'm going to have 3x over 2x minus 1 over 2 times 3x over 2x minus 1 minus 3. So let's multiply in that 2. So now you have 3x over 2x minus 1 all over 6x over 2x minus 1. And now at the same time, I'm going to need a common denominator. So I'm going to multiply 2x minus 1, 2x minus 1, and I'm going to multiply this negative 3 into there. So I get minus 6x plus 3, and then it's all over the same denominator, 2x minus 1. Now here's the algebra that I'm going to take for granted. If you have the same denominator in a fraction made up of two fractions, you basically have this scenario, 1 over 2 divided by 3 over 2, right? Except it's written like this. But what happens in this notation? It becomes 1 over 2 times 2 over 3. The 2's cancel and end up with numerator over numerator. So that's what's going to happen here. This cancels with this, and I end up with numerator over numerator. So that's what's going to happen here. This cancels with this, and I end up with 3x over 6x minus 6x plus 3, which is 3x over 3, which is awesome. It's just x. That's exactly what I was hoping for. So that's the trick of what we call complex fractions, where it's a fraction made up of fractions. So that will be the extra piece of algebra. Now let's check the other way. So we're going to check this one. So in this case, I'm going to plug in 3 times x over 2x minus 3 all over 2 times x over 2x minus 3 minus 1. Now, I'm going to need a common denominator again for the 1, but this time it's going to be 2x minus 3 over 2x minus 3, and don't forget you're multiplying in a negative. So my next step down will be, I'm going to multiply that in, I'm going to multiply that in, 3x over 2x minus 3 over 2x minus 2x plus 3 all over 2x minus 3. And again, the denominators are the same. So I'm left with 3x over 2x minus 2x plus 3, which is 3x over 3, which, yes, yeah, x, boom, I got it. So they are inverses, and we have the domain and range of both. So in your notes, I've added an additional example, so feel free to have a look through there. I'm not going to do it on this video. It's going to be long enough. But now we're going to look at how do we graph inverses. And there is a piece worth talking about. An inverse is reflected over the line y equals x. But the more pertinent and more helpful piece is that if you have the point AB on your original function, so here's an example, this point here, my original function is 1, 0, it becomes BA on the new function. So you just swap the coordinates, and you can see there it is. So if you have a graph with a bunch of coordinates, just swap them and you're good to go. Now, sometimes that'll involve having a restricted domain. So let's have a look. So here we have an original function y equals, or g of x equals x squared, but we have a domain restriction that we only exist in negative values of x, which means we have a point at 0, 0, we have a point at negative 1, 1, negative 2, 4, negative 3, 9. So my graph is restricted to looking at just that side of my parabola. Now, algebraically, what we'll do is we will solve for the inverse, and we get this. Plus or minus root x. But if we look at the domain restriction of our original, right, what do we get? We get a domain restriction that x is less than or equal to 0, which means we have a range of y is greater than or equal to 0. So that means the domain of this one has to be x is greater than or equal to 0, which means what we have is we have to have negative x values only, because if x is greater than or equal to 0, positive x values, that's a positive number, and we need that. Otherwise, we couldn't have the radical. But you'll also notice the domain of my original, x is less than or equal to 0, gives me a range of y is less than or equal to 0, which means all of my outputs must be negative. So if I look at the plus or minus value of this radical, that's what would give me this, y equals. So it would give me something that kind of looks like this, right? But I'm restricting my domain so that I'm only going to have negative outputs. That is what allows me to graph this inverse. I'm only going to keep the negative portion of my radical because I have to satisfy my range restriction. So that means I would graph this as only the negative value, so a reflection in the x-axis of my root x's, which means my graph is going to look down here. But if we just flip our coordinates, negative 1, 1 becomes 1, negative 1, and negative 2, 4 becomes 4, negative 2, and there is my inverse. And it only exists like that because of the restriction in the domain, which gives us a restriction in the range, which gives us a restriction in the domain of our inverse. You can see everything is connected. So let's look at one more graph here. So here we have the graph. It's a linear equation, y-intercept of negative 3, slope of 2 over 1. So we kind of look like this. Those are the points on my graph. So there is my original function. I don't have a ruler, so I apologize. But what we have is we have some coordinates that we can consider. 0, negative 3, 1, negative 1. So rather than do this by solving first, let's actually just swap all these coordinates and see what happens. So then we have 2, 1, 3, 3. You'll notice nothing's going to change on that one. And then here we have 4, 5. So if we swap all of those coordinates, we will have 5, 4. So we'll have a point here. 3, 3 doesn't change. 2, 1 becomes 1, 2. So there. And then we end up with negative 1, 1. And then we end up with negative 3, 0. So that is the coordinate swapping of what my inverse should look like. So what we'll do is let's look at it algebraically and see if that works. So y equals 2x minus 3. So x equals 2y minus 3. X plus 3 equals 2y. X plus 3 over 2 equals y. And now to make that into more of a natural slope-intercept form, it's x over 2 plus 3 over 2, which means we have a slope of 1 over 2 and a y-intercept of 1.5. So look at that. There's my y-intercept of 1.5. And if I were to go up 1 over 2, up 1 over 2, it's all going to work and it looks perfect. So you can do it either way. The swapping of the coordinates is definitely the quick version. So now how do we consider this with transformations? Well, it's exactly the same way we looked at transformations in our 2 videos for section 2.4, but the first step is going to be to swap our coordinates. So here we have inverse function. So my point AB becomes my point BA. Boom, done. Here I have inverse function and then a transformation. So my point AB becomes BA, but then my x value, or in this case my b value, has been shifted 1 to the right. So b plus 1a. So it's the same idea. We just do the inverse swap first. So AB becomes BA, but then I have a vertical shift, so I end up with A plus 1. And then the last one here makes us think a little bit about our transformations. First, we're going to switch to BA. Then my x values are multiplied by a factor of, wait for it, 1/3. And my a value is reflected, or in this case, my y value, but my a component is reflected and multiplied by a factor of 2. Boom. So it works exactly the same way as it was working. We just swap our coordinates first. So there you go. That is your video on inverse functions. You know me, I'm a nerd. It's interesting. I like it. It's fun. I hope you enjoyed it. And watch it as many times as you have to. Thanks so much.